Alright, picking up in part 2 of our derivative as a function exploration, we tip off with the number e. So e is a unique situation. E itself is simply a constant, 2.718, and the numbers will continue, but the exponential as a function has a unique derivative. Now, probably in AP Calc, regular Calc, this is how your teacher wrote it, and the derivative of e to the x is e to the x. But I am not fond of leaving things as x, because x is a function, and I think that's something we often take for granted. So it's really e to a function of x, because it shouldn't matter whether it's x, x squared, sine of x, x cubed, a rational function. It's some function as the exponent. So with this new, new structure, and we take the derivative of the exponential, we have the original exponential times the derivative of whatever the function may be. This should alleviate some serious issues later on down the line when you start coming into contact with some more advanced functions. But we're going to wrap up with a topic that often can become misconstrued. So if a function is differentiable at some particular x value, then we can say that the function is continuous at that value. So think back to limits, right? We had to satisfy the limit from both the left and the right side in order to imply continuity. Same thing here with differentiability. We're going to do a proof of this statement. Bear with me. Okay. So, based on that definition, if f is differentiable at x equals c, then the following limit exists. The limit as x approaches c of f of x minus f of c x minus c equals f prime of c. Right, because that's the assumption we're making, right? If the function is differentiable, that has to be clear. Okay, so this is where we start, and we need to demonstrate that the limit as x approaches c of f of x is equivalent to f of c, because this is the definition of continuity. So, consider, and I'm probably going to have to wind up erasing, so be mindful of that. Consider we have the difference quotient is equal to the difference quotient, right? This is like saying 2 equals 2. Assuming x does not equal c, right? Because then we would have undefined difference quotients. Okay. Let's multiply this denominator to this side. Okay. So what's going to happen, okay, is I'm going to make that algebraic manipulation and subsequently take the limit as x approaches c of both sides. So our next line should look like this. Okay. And your initial thought would maybe to cancel the denominators, but what we really want to do is we want to separate these two into the limit using our product law of limits. Okay, and at this point you might be saying, well, isn't this still undefined? But remember, based on the definition of differentiation, this is equal to the derivative, and this is a continuous function, therefore we can substitute c, and c minus c is 0. So this is really equal to 0 times f prime of c, which is ultimately 0. So the limit as x approaches c, f of x minus f of c is equal to 0. We can now say, I'll take it home with a final color. Alright, remember what we were trying to satisfy? That we're trying to satisfy this. Okay. So we can now say that the limit as x approaches c, f of x, is equivalent to the limit as x approaches c of f of x minus f of c plus the limit as x approaches c of f of c, which, based on this piece of logic here, would yield a 0, and thus at this particular function, at this particular value, we're going to be left with whatever our function output is. So we yield 0 plus f of c, which is equal to f of c. Thus, validating and verifying that if a function is differentiable at a particular point, it implies continuity. Now, can we assume the latter? Can we assume that if a function is continuous, that it is differentiable? Can we assume the converse, that continuity implies differentiability? Tough call. The answer is no. Now, for you calc novices, you might start screaming sharp point, sharp turn, right? But these are mnemonic devices that your teacher embedded in you that didn't necessarily speak as to the depth of conceptual understanding as to why it is not feasible. The easiest function to demonstrate this with is the absolute value function, which looks as such. Right? The reason, right, continuity does not imply differentiability, because this is continuous. Okay? But the way we think about it is something that we call local linearity. And what that says is, as you hone in, right, at a particular data value, so we're going to hone in here at x equals 0. The graph, as you zoom in, should appear more and more to sync with actually not sync, say merge with the tangent line, okay? If you continued, right, if you put this in the right stroke and you kept zooming in, right, and even you can go to Desmos, right, and if you keep zooming in, keep zooming in, keep zooming in, there's always going to be this little V, right? So the tangent line, no matter how you draw it, okay, will never be able to fully satisfy this V-shape effect as compared to a function like a cubic, right? If I have a tangent line at this point and I zoom in, eventually the tangent line and that function are going to coincide with one another. Okay? That's this idea of local linearity, okay? Which is why I recommend getting a little bit more familiar with different functions and their behaviors. Okay? Another function that we typically see this with is x to the 1/3, because at that point, right, same thing, x equals 0, we wind up having a vertical tangent line and why is this such a big deal? Well, the slope is undefined. So if the slope is undefined and you want to take the derivative of that function, then what do you set it equal to? So just because a function is continuous doesn't mean that it's differentiable, and this is critical. More often than not, you're going to experience most functions that are continuous are differentiable, but there are a few, in addition to some piecewise functions. The biggest thing I have with piecewise functions is you have this vertical tangent line instance, but I like to think of like local linearity. Okay, if I know that I have some type of awkward function, absolute value functions, rational exponent functions, it sets off a little thing in my head, think about how the behavior, maybe a quick sketch, and just make sure that there's some evidence of local linearity at a particular point, right? Because I can say that, at x equals 4, yeah, the tangent line would wind up looking like the overall function, but it all depends on that particular data point that you are examining. So continuity does not imply differentiability. So once again, I had mentioned that x to the 1/3 and absolute value of x are those two textbook functions that we know are continuous over the real number system, but not differentiable at x equals 0. But how can we utilize some calculus concepts to assist us in validating that, known knowledge? Because oftentimes, we're told these things and we're told them and we take them for granted, but we don't necessarily have a solid foundation for the applicability of calculus concepts that we've come across. So, how do we ensure that this function is differentiable, or how do we validate that it's not differentiable at x equals 0? Well, rely on our definition of the derivative, right? So the limit as x approaches a, since we have a defined data point of f of x minus f of a all over x minus a, but with a being 0, this makes things significantly easier, right? This is 0, that is 0, and this is 0. Well, 0 to the 1/3 power is 0. So we're left with limit as x approaches 0 of x to the 1/3 f of x divided by x. And utilizing your knowledge of limits, you should be able to see that this function is really behaving like this, or its derivative is really behaving like this. And if we substitute this in, right, this 1 divided by 0 factor is going to tend towards infinity, indicating the limit does not exist and the function is not differentiable at x equals 0. Now, had we simply changed this to a 1, we would probably see a different type of conclusion or an ending. But remember, continuity does not imply differentiability. Right? And if you ever need verify it, go back to the beginning. Go back to the definition of the derivative, because that is the crux and the foundation for which this entire idea or concept is built upon. But we will pick it up with some more rules. Power and quotient rule coming up next.